Well, good afternoon. It is Chemistry B, Unit 6, States of Matter and the Gas Laws. This is day 1. Let's get started. Okay, as you know, matter is made up of 3 main categories: solids, liquids, and gases. And we can categorize these based on many different ways, and one way that we will do this is based on how their particles are arranged and how they interact. Alright, we'll start first with gases. Okay, there's an idea out there, it's called a theory, kinetic theory, that all matter has tiny particles that are always moving. Doesn't matter if it is the table that you might be sitting at right now at home, or the book that you might be writing this on, or the paper. The particles inside that paper are always moving. Now, we cannot see it in a solid very easily, but when we look at it when we look at gas, we can understand that. That's pretty easy to understand, that those particles are always moving. But in a solid, it's very difficult. But the kinetic theory says that all matter, solid, liquid, or gas, is made up of tiny particles, and they are always moving. Okay? Gas particles, we call those molecules, or they could be atoms. So gas particles can be molecules or atoms. And there are 3 basic assumptions, or 3 things that the kinetic theory assumes about matter. Number 1, particles and gases are small, hard spheres that basically have no volume. One of the analogies that I like to use in class is you don't need to understand that if you pull out one piece of hair from your head, it's probably not going to make a whole amount of difference about how your hair is going to look. But you definitely have changed your hair because you've pulled out one piece. And the matter would be the same thing. Pulling a piece of hair off your head is going to change the amount of matter that you have in your system, total system, but as you know, it's not going to make a difference, so it's basically insignificant. Alright, so particles and gases are small, hard spheres with basically no volume. Number 2, the motion of gas particles is fast, it is constant, and it is random. In other words, always moving. They don't know where they're going to go, and they never stop, and they're extremely fast. And this is the reason why gases will fill their containers. This is the other reason why you are able to smell a skunk before you see a skunk, if it is sprayed or if it's been hit by a car or something along those lines. It's also the same reason why if you walk down the freshman hallway and somebody has sprayed a bunch of perfume, you could smell it around the corner, and you know somebody's had a perfume attack because gas particles attach to the odor. And the odor, the gas particles move fast, constant, in all different directions, and before you know it, the whole school smells like the perfume department at Macy's. This is also why we can smell gas when it's on. When it is shut off, eventually we can't smell it anymore. Natural gas is odorless, but the gas company puts in that sulfur odor. So if you've ever smelled natural gas and you think, oh, there's a sulfur odor in there, that is on purpose so that you can smell it, and that uses the ideas of the kinetic theory. And number 3, all the collisions between the particles in a gas are perfectly elastic. Kinetic energy transferred from one particle to another without the loss of energy. Okay? Perfectly elastic means energy is transferred from one object to another, and it's seamless. Alright. With gas, we know that there can be pressure. Alright? So the next topic we're going to talk about is gas pressure. Pressure in a gas is caused from the force that is exerted by the gas per unit surface area of an object. That's the textbook definition. Okay? What causes gas pressure? Simple. Simultaneous collisions of billions of rapidly moving particles in a gas with an object. So all those particles that are inside a container or inside a room are smashing into each other, and they're colliding many times, and there's so many of those particles that it causes pressure. It causes even more collisions. Is there an area that does not have particles? Yeah, there is. We call it a vacuum. All right, it's an empty space. It has no pressure. If there's no particles, you can have no pressure. Now, the only place that is natural that has a vacuum is space. There's no air in space, but there's no matter in space. So that is the only naturally occurring vacuum. Now, we can create a vacuum in the laboratory, but it's not naturally occurring. Okay? Now, you've heard of this term, atmospheric pressure. You've all probably experienced atmospheric pressure. It's certainly very familiar to us, especially if you've gone into the mountains. All right, and atmospheric pressure is caused by the colliding atoms and molecules and hence the air. That's called atmospheric pressure. All right. These atmospheric pressure, as you know, decreases as you move away from the Earth. And why is that? Because there's less density. Well, if there's less density, what does that mean? That means that there is less particles. So as you move away from the Earth, there are less particles. It's less dense. Less dense means less pressure. Okay? So you've heard the term, when you go into the mountains, the air seems to thin. Well, that's kind of what it does. All right? What measures air pressure? A barometer, of course. The unit of measure that we use for measuring air pressure is called the Pascal. Atmospheric pressure, air pressure, the same thing. All right? Normal atmospheric pressure is about 100,000 PA. All right? And the standard temperature and pressure is a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals. All right? That's STP, standard temperature and pressure. You are going to need to know that. Temperature is 0 degrees Celsius and the pressure is 101.3 kilopascals. All right, kinetic energy and temperature. Particles absorb energy and store it in the particle itself, but the temperature does not raise. Okay, so what does this mean? All right, so we have a particle, and it's just sitting there, and now it gets bombarded with a whole bunch of energy. Well, that particle has the ability to absorb some of that energy, and as it absorbs that energy, it stays, the particle itself absorbs that energy, but the temperature in that particle does not raise until it can absorb no more energy. All right? The rest of the energy will speed up the particles, which then increases the temp. Average kinetic energy is the particles of atoms and molecules at a given temperature have wide range of kinetic energy. Most of the particles are in the middle range. So we have some that are moving fast, some that are moving slow. Now here's a key. The physical state of matter does not change the average kinetic energy. Average kinetic energy and Kelvin temperature. Let's take a look at this.
1 times scale goes like this. So it's a balloon. You heat it up, all the particles inside get all jiggly, and the whole thing expands because they're all flying around it, pushing it in the inside, which makes it expand. And then if you cool it, it does the opposite, it gets smaller. And they notice this line, this lovely line pattern happening, this relative size, the volume, and the temperature. So then they dropped the temperature a little bit more. I went down to about -3, really cold day, -5. Kept going in line. So they were like, hang on, we have rulers, we can continue this on. We don't even need a machine that goes down to -200. We can just continue this. They drew a line, and the line went all the way down here, all the way down to this point at -273. They declared absolute zero. Now, it's a bit of a bold statement to just go, well, you can't go below that, that's absolute zero. But, you know, you should be able to get as cold as you want, surely. Except for this really interesting thing we found out. Look, if you actually see this is a volume here, and yeah, I can imagine this is something really cold, a balloon down here, which would be really tiny, super tiny balloon. But if you were just to look at the volume, so just I'm on the temperature for a second, just look at the volume of these balloons. They're getting smaller each time as they go down here. And what happens when you cross this axis? You get into minus volume. That doesn't make any sense. That makes my head sore. Yeah, an inside out inverted balloon. And then there wouldn't even be balloons, it would be everything. Liquids turning into nah, it doesn't exist. As far as I know, it doesn't exist. So yeah, it looks like this here -273 is the bottom of the bucket. That is absolute zero, and it turned out to be pretty true in most places. For example, outer space. Outer space is 270, and not even the bottom. 273 -273. So, alright, all they did then to fix this into something, because it started to look a bit weird here, they wanted to make a proper temperature scale, because it suddenly became embarrassing that the bottom wasn't zero anymore. So they got 0 on the Celsius scale, and they did what any person in school would do, and their graph looked a bit wrong. They wait till the teacher's not looking, and they just go, let's just drop everything 273 to the left, that will fix that. We just kind of went, yeah, here we go, fixed. And we just cover that bit there. There's nothing below 0, so happy days. So what they did was they took this text and they put it over here, and they drew a line, and before anyone could come back and look at their graph, they were like, wait, hang on, we've almost got this. We'll just get a white marker here, and just, yeah, here's my white pen. Yeah, excellent. Ta-da! I have a new temperature scale, and now it goes at 0 and goes absolute 0. You can't go below this one.
Okay, so that was a somewhat humorous way to talk about the Kelvin scale. All right, and as we look at particles, we know that as they cool, they will slow down. All right, and as they slow down, the theory says they will eventually stop, and when they stop, that's called absolute zero. All right, absolute zero is a so far it is a fictitious place here on Earth. They've gotten really close, but they have not declared absolute zero in a laboratory setting. But as the particles cool down, they will slow down, and when if they stop, that will be called absolute zero. Absolute zero, as I said, has not been achieved in the lab, but it is close. The Kelvin scale incorporates absolute zero, starting the scale at 0. Okay? Kelvin temp is direct proportion to the average kinetic energy of the particles of the substance. 0 is no movement at all, and as you saw in the diagram, 273 is where it all starts. 273 is freezing, 373 is boiling. Okay, and that's our unit.